Hello. So today we will start with random variables and expectance and variance. So let's start. So first we'll start about why do we need even random variables? Why? So basically let's say we have two dice and we roll them and we say what is the probability that some of those dices are equal to 7. So see, what we need to find out is that P of sum equal to 7. Are we really bothered with what the sums are? So basically we don't need to know if the sum is 2 5 or let's say 4 3, right? So here the thing sum, right? Here the thing sum is called the random variable, as simple as that. Okay, so basically let's say this thing you can write as P of, okay, so let there be a symbol. Let's say let x be the random variable such that it denotes the number of heads, and we are tossing 3 coins, right? So what can be the possible? P of x equal to 1, or P of x equal to 1, or P of x equal to 2, or P of x equal to 3. What does these all mean? Basically P of x equal to 0 means what? Means wherever the number of heads between 3 coin tosses, right? So 3 coin tosses are 0, as in meant tail. So what will this be? This will be 1 by 8. The next one will be, this will be 1 by 8. The next one will be what? 1 head means head tail head tail head. 3 by 8. The next one can be what? Head tail tail head. So 3 by 8. The last one can be 1 by 8 head. Simple logic. Okay, so this is what basically in short what random variable means. Okay, so if you notice something, right, so these variables are very much discrete. Okay, so these are discrete random variables. What do I mean by discrete? So discrete, simple meaning, we will get into discrete versus continuous a bit later on. So simply discrete means, let's say this is a graph, right? And let's say there is a graph like this. Wait, let me draw this well. Okay, so this is, let's say these are 2 graphs I have. Okay, so here you can see for each value so for each value of x I have some value, for each value of x I have some value, right? Okay, but for here, for each value of x, do I have some value? No, for specific values I have. So these are basically discrete. This is called discrete. Okay, and this is the continuous. This is the main difference. Okay, so here can you notice something? Here what we are doing, here we are, wait, let me do this. Yeah, so here if you notice something, here all of them are discrete. For we are just checking them at 0 1 2 3. So P of x equal to 0.2.5 does not make sense here, right? So here we have something called the discrete random variables. Initially we are going to get into discrete random variables. So from discrete random variables we must define something called the probability mass function. Probability mass functions, what does that mean? It means the P of A is, if I say what is the probability mass function, PA of x is equal to P of x equal to A. Okay, so basically what does this mean is that for P of A, whatever the value of A is, so basically if this is the, let's say, wait, so here let's say at 2, the P of 2 will be P of x equal to 2, as simple as that. So now logically every probability few things. Okay, so all the probability must be greater than 0. Okay, that is very thing. And okay, So whatever in the range, of course. Okay, so basically let's say my range is still x1, x2, x3 till xn. So in this range the values will be these. Okay, but without this range, what will the value be? P of a will be 0. So for other cases the probability is 0. So only in the range I'll have some probability greater than 0. And logically you can also see the sum of all probabilities has to be 1. Okay, simple logic. So probability mass function can be defined as something like, you can also, like, let's say I have some p of 0 to be 1 by 4, p of 1 to be half, p of 2 to be 1 by 4. So let this be my scenario. Okay, then see this. So basically how will this look like? Something like this. And let's say this will be the first thing, and then this will be the second thing, and then this will be the third thing, right? So here you can see, for this will be for 0, this will be for 1, and this will be for 2. Okay, so this is what? This is 1 by 2 here, and this, so 1 by 4 here and 1 by 2 here. Okay, and they all sum up to be 1. So graphically you can see this is a very beautiful thing, how we can approach, let's say, probability mass functions. Okay, so now we'll do a beautiful sum that will help you understand how this shit works, and let's start. So this is the sum. Okay, so probability mass function is given by this, where that is some positive value. Find px equal to 0. Okay, px equal to 0, how will you find it out? Okay, so since it's a probability mass function, then we know something that, let's say, summation of whatever the probabilities are, it has to be 1, right? So now what can we do? Summation of this equation, c lambda I by I factorial, has to be 1. Okay, c is common, you can take out c common here, right? So what is my what does this look like? Lambda I by I factorial summation. Have you seen this before? This is nothing but e to the power lambda, e to the power x expansion. Okay, so now from this we can write what? C e to the power lambda is equal to 1. Okay, so my c will become e to the power minus lambda, right? So now let's calculate px equal to 0. So px equal to 0, px equal to 0 will be what? C lambda to the power I. What is I here? I here is 0, right? So 0 by 0 factorial. So c is what? E to the power minus lambda. This lambda to the power 0 is 1 by 1 factorial. So that is what? That is nothing but e to the power minus lambda. So the first answer is e to the power minus lambda. Now p of x greater than 2. So logically p of x greater than 2. I'm solving this fast. I think this is very intuitive. P of x greater than 2 is what? 1 minus p of x less than equal to 2. Right? So what is that? 1 minus p of 0 plus p of 1 plus p of 2. Right? This is the scenario. So this becomes what? 1 minus e to the power lambda, we just calculated it, minus e to the power lambda minus e to the power minus lambda minus e to the power minus lambda square by 2 factorial. Okay, and you can solve it here from now. I am not solving this after this. Did you understand how to solve these kinds of problems? I just gave you a simple example, very simple example, how to solve any like probability mass function questions. Okay, so this was a very short example of how we approached it. Now we will talk about a very interesting topic that is called expectation. Okay, So how does expectation happen? What is expectation? Why did we even need expectation? So a simple example, okay, simple example. So let's say I have a huge value, right? So let's say I have 100 ones and 1 0. Okay, simple logic. So now the thing that would happen is that this does not like, see, so basically I have two possibilities, 1 or 0, right? So now let's say if I have to tell you to choose something, so you will choose either between 1 or 0, but you know, like statistically it is relevant that there have been 100 ones and 1 0, so logically 1 aane ka chances are very high, right? But when you are given a chance of 1 or 0, you can't perceive that sense of probability through 0 and 1, right? Since they are equally probable, so we come away with something called the expectation. Expectation is something very simple. Expectation of x is nothing but summation of x px, nothing else. Okay, it's the summation of x px. So for example, in this example, what is the expectation of, let's say, x? What x here is, basically x is the random variable. Okay, simple logic. So here what would be x equal to, can be either be 0 or 1, right? So here half of chances, so e of x will be 0 into half plus 1 into half. Okay, then that would be half. Okay, this is very simple. Now let's also find out what is the expectation of let's say dice. Okay, so expectation of dice will be what? 1 into 1 by 6, then plus 2 into 2 by 1 by 6, and so on. So that will be what? That will be, I think, 21 by 6, that is 7 by 2. Okay, so this is very simple. Okay, so basically now, so I'll also explain how this thing would affect more, right? So for example, here it was equally probable, right? So but here it was, for example, in this case it is not very equally probable, right? So what would happen in this case? E of x would, so probability of E of x happening, let's say 0 has a probability of 1 by 3 and 1 has a probability of 2 by 3. So my e to the power ex would become 2 by 3 into 1 and everything. Okay, so basically we get the sense that it is more probable that 1 would be there rather than 1. Okay, so that is the main idea that we get here, okay, of what expectation is. And the sums are very simple like this itself. It's not very difficult or anything. The sums are totally based on this logic. So like for example, if I give you another sum, so let's say there is a x random variable which takes the value -1, 0 or 1. Okay, and -1 is taken how many times? -1 is taken 0.2 times, 0.5 times, 0.3 times. Now you have to find out what is the expectation. Find the expectation of x square. Okay, how do you find it? How do you find it? Can you think of something? So you can think of it something like this. Okay, simple thing. So now we can replace this as e to e of y is equal to what? Y px, y py, where y is x square. So what is the probability of y? Y can either be 0 or 1, and that is both 0.5, right? So here expectation of y would become equal to 0.5, right? But logically, if you had done this silly mistake, e to the power x square, what would be e to the power x? So e to the power x would be 0.1. So you notice something, that e to the power x square is not equal to e to the power x whole square. So don't confuse this. You cannot just like square it like this. Okay, so you understand this, right? So from this, do you understand something? Like if there is a function there, we can also substitute that function in. So can we use this to find something very innovative? Okay, so let's prove a theorem. Okay, so that we can understand this concept. I just gave you a very highlight into the feature, but let's get into the theorem and understand how this works in detail. Okay, so the proposition that I have is very simple. So this is my proposition. So the main idea of the proposition is that I can put any function in it. So basically, let's try to verify the piece of thing we did, right? So let's say I had what? Yeah, so I had like e to the power x square. So e to the power x square said I can put the function there. So minus 1 whole square. So it would be minus 1 whole squared into 0.2 plus 0 square into 0.5 plus 1 squared into 0.3. So this would become what? 0.5. So this formula works. Okay, but how does it work? Like the proof is not that important, but I think everybody should understand this. So let's reverse prove this. So let's say summation of I g xi p xi. Okay, now how can we break this? Okay, let's zoom in a bit. So now I'll introduce two summations of j and I such that g xi is equal to some xj yj, and I'll replace this thing with a yj. So I'll do yj p xi. So it's the same thing. Okay, so I'm just introducing a new variable j, that's why a new summation has popped up. Okay, so this thing is done. Now I can, since this is a j variable thing, I can pull this thing here and keep the I variable thing here. So I'll keep it j yj summation of I p xi. Wait, why did I scroll? P xi. Okay, and when you do this, so what is this? This becomes summation of j yj, and what is the value of I? This. So value of I is nothing but yj. So this becomes what? P of gx such that is yj. Okay, so this becomes what? Expectation of gx. See, so we derived this. Simple logic, not that of a hard logic to understand. It's a very simple logic how we derive this. Okay, so now this is basically what expectation comes out to be, and yeah, so we'll end it here. We'll continue with variance the next day, and thank you.